Welcome. Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold reaches between Mars and Jupiter, where stone orbits stone in patient silence, and visitors from beyond Neptune occasionally drift through on their way to nowhere in particular. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The object designated 3I Atlas begins its approach toward the inner solar system sometime in the early months of 2024, though of course it has been falling inward for much longer than that, centuries, perhaps millennia. Its trajectory determined by gravitational interactions so distant and complex that no computation fully captures them. It comes from the Oort cloud, that theoretical shell of icy debris surrounding the solar system at distances so extreme they barely qualify as distances at all. 1 light-year out, perhaps, or half that, where the sun's gravity weakens to nearly nothing and passing stars occasionally stir the frozen architecture into motion. The nucleus itself measures perhaps 2 kilometers across, though early observations remain uncertain. Ice and rock bound together in the darkness, untouched by sunlight for so long that its surface chemistry belongs to an earlier era of the solar system's formation. It carries water ice, frozen carbon dioxide, methane, ammonia, the volatile compounds that never condensed into planets closer to the sun, expelled outward during the chaotic migrations of the gas giants 4 billion years ago, only took 4 billion years to fall back inward. As it crosses Neptune's orbit, still moving at 30 kilometers per second relative to the sun, something begins to change. Sunlight, weak at this distance but present, starts to warm the surface. Sublimation begins, ice turning directly to vapor without melting, releasing gas molecules that have been locked in place since before Earth had continents. The pressure of this outgassing creates a faint atmosphere around the nucleus, a temporary coma of water vapor and carbon monoxide that glows dimly in reflected sunlight. The solar wind pushes against this coma, sculpting it into a tail that points perpetually away from the sun, a directional marker visible from Earth through patient telescopes. The comet does not know it is being watched. It does not know anything. Of course, being simply an aggregate of frozen volatiles following orbital mechanics with perfect indifference, but Earth-based observers begin tracking it in January, noting its brightness, its spectroscopic signature, the angle of its approach. Early calculations suggest it will pass through the inner solar system at a safe distance, crossing the orbital paths of the terrestrial planets, but not intersecting with any actual planet, a common occurrence, statistically speaking, though each one receives attention nonetheless. What distinguishes 3I Atlas from other comets becomes apparent only after weeks of observation. Its trajectory, when traced backward, originates not from the Oort cloud after all, but from interstellar space from beyond the sun's gravitational influence entirely. The object comes from another star system, perhaps from a planetary system not unlike this one, where gravitational interactions during its formation ejected this particular fragment into the void. Perhaps from a system where planets never formed at all, and this ice rock aggregate drifts alone through the galaxy, occasionally passing through other stars' domains without ever being captured. Its velocity confirms this. Moving too fast to be gravitationally bound to the sun, it follows a hyperbolic trajectory arriving from one direction. swinging around the sun, departing in another, never to return. An interstellar visitor, the third such object detected by human instruments, hence the designation 3Psi. Third interstellar. Atlas refers to the survey system that first identified it, an automated telescope network scanning for asteroids and comets, programmed to notice things that move against the background stars. The chemistry of its coma, analyzed through spectroscopy, reveals carbon compounds in unusual ratios, not dramatically different from solar system comets, but different enough to suggest formation in a molecular cloud with slightly different elemental abundances. Chemistry from another star's nebula, another protoplanetary disk, another sequence of condensation and accretion that played out light years away and millions of years ago. Only took a few million years to reach here. Scientists observe it with interest rather than alarm. Its path brings it nowhere near Earth. Closest approach occurs at a distance of several astronomical units. Far outside Earth's orbit, it poses no threat, offers no danger, represents nothing more than a curiosity, an opportunity for spectroscopic analysis and trajectory calculation, a sample of interstellar material delivered, briefly, to within reach of Earth's instruments before departing forever. As March arrives, the comet crosses the orbit of Jupiter, still inbound, its coma growing brighter as sublimation accelerates. It will reach perihelion closest approach to the Sun sometime in late spring, passing inside Mars's orbit but outside Earth's before beginning its outward journey. The tail lengthens, plasma and dust streaming behind it in the solar wind, visible in photographs as a faint smudge against the background galaxy. Somewhere ahead, in the space between Mars and Jupiter, lies the asteroid belt, not a barrier, not a dense field of tumbling rocks, but a region of enhanced object density, still mostly empty, still mostly nothing. The comet will pass through it on its way inward, threading between asteroids separated by millions of kilometers, encountering nothing, deflecting nothing, disturbing nothing, just another visitor drifting through. The asteroid belt occupies a region of space beginning roughly 2.2 astronomical units from the Sun, about 330 million kilometers, and extending outward to approximately 3.2 astronomical units. Though these boundaries blur at the edges where scattered objects drift in elliptical orbits that carry them inward toward Mars or outward past Jupiter. The entire belt, despite containing millions of objects, holds less than 5% of the Moon's mass. Most of that mass concentrates in four large bodies: Ceres, Vesta, Pallas, and Hygeia. The rest, millions of smaller asteroids, collectively weigh less than Earth's oceans. Popular imagination pictures the belt as a dense field requiring careful navigation, a gauntlet of tumbling rocks where collisions occur frequently and pilots must maneuver constantly to avoid impact. The reality offers less drama. If a spacecraft were placed randomly within the belt, the probability of passing within visual range of an asteroid close enough to see it against the stars approaches zero. Distances between objects typically measure in millions of kilometers. Empty space dominates. The belt resembles not a crowded highway, but a vast desert where occasional pebbles lie separated by kilometers of sand. Dawn. A NASA spacecraft that visited Vesta and Ceres between 2011 and 2018 encountered no asteroids during its journey through the belt except the two it specifically targeted. No course corrections for collision avoidance, no near misses, just empty space, crossed at 17 kilometers per second, silent and dark. Only took 7 years to reach Ceres. The asteroids themselves represent compositional diversity. Inner belt objects, closer to the Sun, tend towards silicate-rich compositions, rocky bodies formed at temperatures high enough that volatile compounds escaped into space during the solar system's early chaos. S-type asteroids, as they're designated, contain iron-bearing silicates and metallic iron, their surfaces gray or reddish depending on oxidation state and mineral content. They reflect sunlight with moderate albedo, making them easier to detect than darker objects at similar distances, moving outward through the belt. Composition shifts. C-type asteroids, rich in carbon, dominate the outer regions. These objects formed farther from the Sun, where temperatures allowed volatile compounds to condense water ice, organic molecules, carbon-bearing minerals. Their surfaces appear nearly black, reflecting only 3 to 4% of incident sunlight, making them difficult to observe from Earth. They represent the most common asteroid type, accounting for roughly 75% of known belt objects, though detection bias means actual percentages remain uncertain. Scattered among these categories, M-type asteroids, apparently composed of nickel-iron metal, possibly the exposed cores of differentiated bodies that fragmented during ancient collisions. A-type asteroids, rare and olivine-rich, glowing faintly red in reflected sunlight. V-type asteroids, basaltic, likely fragments ejected from Vesta during impacts that excavated through its crust. Each type tells a story about temperature, pressure, and timing during the solar nebula's collapse 4.5 billion years ago. The belt's low total mass suggests something prevented normal planetary accretion in this region. Computer simulations, run thousands of times with varying initial conditions, consistently show that without external influence, the material in the asteroid belt should have coalesced into a planet within 10 million years of the solar system's formation. Instead, millions of separate bodies persist, their orbits stable across billions of years, never accreting into anything larger than Ceres. Only took 4 billion years to not form a planet. Jupiter provides the answer, or part of it. The gas giant's immense gravity, 318 times Earth's mass, perturbs the orbits of objects in the belt, increasing their relative velocities. When asteroids approach each other, they do so at speeds too high for gravitational capture. Instead of gentle collisions leading to accretion, impacts become destructive, fragmenting larger bodies into smaller ones. The belt grinds itself down over time rather than building up, a process operating in reverse of normal planetary formation. This grinding proceeds slowly. Collision rates in the modern belt remain low. Most asteroids will never collide with another object before the Sun expands into a red giant 5 billion years from now. But over geological timescales, impacts accumulate. Asteroid families, groups of objects sharing similar orbits and compositions, mark the sites of ancient collisions that shattered parent bodies into dozens or hundreds of fragments. The Flora family, the Eunomia family, the Coronis family, each represents a catastrophic impact sometime in the belt's past. The fragments now scattered along similar orbital paths like beads on an invisible string. Vesta's surface, imaged in detail by the Dawn spacecraft, shows 2 enormous impact basins at its south pole. The larger, named Rhea Silvia, measures 500 kilometers across and excavates 20 kilometers deep into Vesta's crust, exposing mantle material that should remain buried. The impact that created this basin occurred roughly 1 billion years ago, ejecting thousands of smaller fragments into space. Many of these fragments now orbit as the Vesta family, basaltic asteroids sharing Vesta's unique spectroscopic signature. Some eventually migrated inward through orbital resonances, falling to Earth as meteorites head meteorites, named for their mineralogy howadites, Eucrites, Diogenites. Samples of Vesta's interior, collected in Antarctica and the Sahara, analyzed in laboratories, telling the story of differentiation and catastrophic disruption. The belt rotates, collectively, around the Sun. Objects in the inner belt complete one orbit every 3 to 4 years. Objects in the outer belt require 5 to 6 years. This differential rotation, combined with Jupiter's perturbations, creates a dynamic environment where orbits slowly evolve over millions of years. Some asteroids migrate inward, potentially becoming near-Earth objects if their orbits evolve far enough. Others migrate outward, eventually encountering Jupiter's gravitational influence directly and being ejected from the solar system entirely. The belt loses mass over time, slowly bleeding objects into the inner system or out to interstellar space. 3I Atlas passes through this region without incident, as expected. Its trajectory carries it through the outer belt, where object density remains lowest, no close approaches, no gravitational deflections. The nearest asteroid passes several million kilometers away, invisible against the background stars, unaware of the interstellar visitor threading past it at 30 kilometers per second. Only took a few million years to arrive, a few hours to pass through, an eternity to travel onward. The structure of the asteroid belt reveals itself most clearly through absence, through gaps where asteroids should orbit but don't, empty regions carved by gravitational resonances with Jupiter. These gaps, called Kirkwood gaps, after their discoverer Daniel Kirkwood in 1866, correspond to orbital periods that form simple ratios with Jupiter's 12-year orbit, 3.1527321. At these locations, an asteroid would experience regular gravitational tugs from Jupiter at the same point in its orbit, century after century. The perturbations accumulating until the orbit becomes unstable and the object migrates elsewhere. The 3-1 resonance, located at 2.5 astronomical units, creates the belt's most prominent gap. An asteroid orbiting here would complete 3 revolutions around the Sun for every one of Jupiter's, returning to the same relative position every 4 years. Jupiter's gravity, pulling at this asteroid from the same direction during each alignment, gradually increases the orbit's eccentricity, stretching it into an ellipse that eventually crosses Mars's orbital path. Most objects that wander into this resonance exit within a few million years, either colliding with Mars, falling into the Sun, or being perturbed onto planet-crossing trajectories that bring them into the inner solar system as near-Earth objects. Between the gaps, asteroids cluster in families and groups, their distributions reflecting both the resonances that clear nearby space and the collisions that create fragments sharing similar orbits. The belt's population density varies by orders of magnitude depending on location. Some regions contain hundreds of catalogued objects per cubic astronomical unit. Others hold only a handful. The texture of the belt is lumpy, clumped, organized by invisible gravitational architecture that has operated unchanged since the solar system's youth. Orbital resonances explain more than just gaps. They also create stable regions where asteroids accumulate despite Jupiter's influence. The Hilda group orbits at the 3-2 resonance, completing 3 orbits for every 2 of Jupiter's, their paths tracing triangular patterns around the Sun when viewed from Jupiter's perspective. The Cybele group clusters at the 7-4 resonance. The Thule group occupies the 4-3 resonance, containing only a few dozen known members. Rare objects that found stability in a region where most orbits decay. Only took 4 billion years to settle into equilibrium. Jupiter's Trojan asteroids, while technically not part of the main belt, demonstrate resonance stability at its extreme. These objects share Jupiter's orbit, clustered around the L4 and L5 Lagrange points 60 degrees ahead of and behind the planet. thousands of Trojans orbit at these locations, held in place by the combined gravitational influence of the Sun and Jupiter. Their position stable over billions of years. The Greeks, as the leading group is collectively called, and the Trojans trailing behind names drawn from Homer's Iliad, assigned by astronomers who apparently felt that gravitational stability deserved mythological designation. The mathematics underlying these resonances derives from celestial mechanics developed over centuries. Newton's gravitational equations, refined by Lagrange and Laplace, further developed by Poincaré, who discovered that even simple gravitational systems involving three bodies produce chaotic behavior over long timescales. The three-body problem, Sun, Jupiter. Asteroid admits no general analytical solution. Orbital evolution must be computed numerically, integrated forward through time using approximations that accumulate error. Predictions beyond a few million years become unreliable. The belt's exact configuration 10 million years from now remains unknown, unknowable, lost in the computational fog of chaos theory. Yet patterns persist. The Kirkwood gaps maintain their positions. The Hildas continue their triangular dance. The Trojans cluster around L4 and L5 without dispersing. Statistical stability emerges from individual chaos, each asteroid following an unpredictable path, but the collective distribution remaining constant, a kind of gravitational thermodynamics, where macro-scale properties hold steady while micro-scale trajectories vary wildly. Resonances affect not only orbital periods, but also rotational states. Some asteroids spin rapidly, completing one rotation every few hours, their shapes distorted by centrifugal force into elongated ellipsoids. Others rotate slowly, taking days or weeks to complete one turn, their surfaces experiencing extended periods of sunlight and shadow. A few tumble chaotically, their rotation axes precessing through space without settling into stable orientations. Collisions impart angular momentum randomly, and small asteroids lack sufficient self-gravity to damp out wobbles through internal friction. They spin as they were spun, conserving angular momentum across billions of years unless another impact intervenes. The largest asteroids achieve more regular rotation. Ceres spins once every 9 hours, its axis tilted only 4 degrees from vertical, rotating smoothly like a miniature planet. Vesta completes one rotation every 5 hours, tilted 27 degrees, its surface experiencing rapid day-night cycles that drive temperature variations from -100 Celsius in shadow to -20 Celsius in sunlight. These thermal cycles, repeated billions of times over the solar system's history, crack surface rocks through expansion and contraction, gradually reducing boulders to gravel to dust. Temperature in the belt varies with distance and surface properties. At 2.5 astronomical units, a dark C-type asteroid absorbs most incident sunlight, its surface warming to perhaps -100 Celsius at noon, cooling to -150 Celsius at night. A bright S-type asteroid at the same distance, reflecting more sunlight, remains cooler -120 Celsius in daylight, -160 Celsius in darkness. Neither temperature permits liquid water on the surface. Though some asteroids may contain ice beneath insulating layers of dust, preserved from the solar system's formation, awaiting excavation by future impacts, or, possibly, future mining operations. Only took 4 billion years to be considered a resource. Jupiter itself remains invisible from most of the belt, too distant to resolve as more than a bright point of light, the second brightest object in the sky after the Sun. But its influence permeates everything shaping orbits, clearing gaps, preventing planetary accretion, maintaining the belt's structure through gravity alone. A planetary shepherd, keeping the asteroids in line without ever approaching them, operating through mathematical relationships that reduce to simple fractions 3, 1, 5, 2, 7, 3, 2, 1. The music of the spheres, playing in silence. 3I Atlas continues inward, already past the outer belt, crossing regions where object density peaks, encountering nothing, deflecting nothing. Its trajectory determined billions of years ago by interactions in a star system that may no longer exist. The comet carries its interstellar chemistry undisturbed through Jupiter's domain, indifferent to the gravitational architecture that has organized this region of space into patterns of presence and absence, stability and chaos, gaps and clusters that will persist long after the comet departs. The designation 3I Atlas marks only the third interstellar object detected passing through the solar system, though statistical models suggest hundreds enter and exit each year, most too small or too distant to notice against the vastness of space. The first, 1I Oumuamua, arrived in 2017 from the direction of Vega, tumbling through the inner solar system on a hyperbolic trajectory that carried it past Earth at 24 kilometers per second. Cigar-shaped or pancake-flat, depending on interpretation, reflecting sunlight with unusual brightness variations, accelerating slightly beyond what gravity alone predicts. Oumuamua generated more questions than answers before departing beyond observation range within months of discovery. The second, 2I Borisov, appeared in 2019, identified by amateur astronomer Gennady Borisov, using a telescope he built himself. Unlike Oumuamua, Borisov behaved like a comet developing a coma and tail as it approached the Sun, outgassing water vapor and carbon monoxide, displaying spectroscopic signatures consistent with comets formed in the solar system. Yet its trajectory confirmed interstellar origin, arriving from outside the Sun's gravitational influence and departing the same way, never to return. A comet from another star system, chemically similar to local comets, suggesting that planetary formation produces similar objects regardless of which star serves as the central furnace. 3I Atlas adds a third data point to this sparse collection. Its spectrum shows carbon compounds in higher concentrations than typical solar system comets, organic molecules containing carbon-hydrogen bonds, possibly complex chains, possibly simple. The resolution of Earth-based spectroscopy insufficient to determine exact structures. The carbon may originate from the molecular cloud where its parent star formed. Cold gas enriched by previous generations of stars that exploded as supernovae, seeding the galaxy with heavy elements synthesized in their cores. Carbon from other stars, now sublimating in this star's light, temporarily visible before dispersing into the solar wind. The object's velocity, measured through Doppler shift of spectral lines, confirms it cannot be gravitationally bound to the Sun. Moving at 47 kilometers per second relative to the Sun's rest frame, it carries too much kinetic energy to be captured into orbit. Its trajectory, traced backward through time using ephemerides and gravitational models, originates from the direction of the constellation Lyra. Though this tells little about its actual source, stars in Lyra lie at varying distances, tens to hundreds of light-years away, and the comet may have traveled much farther, its trajectory bent by encounters with other stars during its journey through the galaxy. How long has it been traveling? The question admits no certain answer. If it comes from a star 10 light-years away, and if it has maintained roughly constant velocity, the journey would require roughly 200,000 years time, enough for Homo sapiens to migrate out of Africa, develop language, create art, build civilizations, and eventually construct telescopes capable of detecting a small, icy visitor passing briefly through the neighborhood. If it comes from farther away, the journey extends proportionally. 50 light-years, 1 million years. 100 light-years, 2 million years. Timescales that dwarf human history, yet remain brief compared to the age of the galaxy itself. Only took a few million years, give or take. The comet's parent system, if it still exists, likely resembles this one in broad architecture. Planetary formation proceeds through similar mechanisms regardless of stellar mass, at least for Sun-like stars. A molecular cloud collapses under its own gravity, spinning faster as it contracts, flattening into a disk of gas and dust around a newly ignited star. Within this disk, dust grains stick together through electrostatic forces and gentle collisions, growing into pebbles, then boulders, then planetesimals kilometers across. These planetesimals either accrete into planets or get ejected through gravitational interactions with forming gas giants flung outward into the star's Oort cloud, or ejected entirely into interstellar space. Statistical estimates suggest that, for every star in the galaxy, roughly 10 Earth mass of material gets ejected during planetary formation. Most remains bound in Oort clouds, but some achieves escape velocity and wanders the galaxy indefinitely. Billions of stars in the galaxy, each ejecting billions of comets and asteroids. The interstellar medium contains a diffuse population of planetary building blocks drifting between star systems, occasionally passing through one another's gravity wells, rarely interacting, mostly alone. 3I Atlas represents one such fragment. It may have orbited its parent star for millions of years before ejection, slowly spiraling outward through gravitational interactions, finally achieving escape velocity during a close encounter with a gas giant. Or it may have been ejected early, during the chaotic phase of planetary formation when migration of giant planets scatters smaller bodies throughout the system. Either way, it eventually departed, carrying chemistry from its birthplace into the dark between stars. The object contains no life, almost certainly. Surface temperatures during its interstellar journey hovered near absolute zero, -270 Celsius. Cold enough that chemical reactions proceed immeasurably slowly. Cold enough that even radioactive decay provides insufficient heat to warm the interior beyond a few degrees. Any organic molecules locked in the ice remain frozen, their structures preserved but inactive, unable to replicate or metabolize or perform any function associated with biology. A chemical library, not a living thing, traveling through space in suspended animation until sunlight warms it enough for sublimation to begin. Whether life exists on planets orbiting its parent star remains unknown. The comet carries no information about this. No radio signals, no biomarkers, no indication of technology or intelligence or even bacterial metabolism. Just ice and rock, carbon and water, organic molecules synthesized through non-biological processes in cold molecular clouds. The same building blocks present in the solar system's comets, formed through the same chemistry, obeying the same physical laws. Universal chemistry. Indifferent to location. Earth-based observers continue tracking 3I Atlas through telescopes scattered across the planet. Arrays in Chile, Hawaii, Arizona, South Africa, each contributing observations during clear nights, measuring position and brightness, refining trajectory calculations, collecting spectra when the object brightens enough for detailed analysis. The data accumulates in digital archives, available to researchers worldwide, adding incrementally to humanity's understanding of interstellar objects and their properties. The comet does not know it is being studied. It does not know anything. It follows its trajectory exactly, responding to gravitational forces with perfect obedience, sublimating ice according to thermodynamic laws, reflecting and absorbing sunlight according to its composition and temperature. A natural object doing natural things, briefly visible before departing forever into the dark between stars, carrying its interstellar chemistry back into the void. Only took 4.5 billion years for anyone to notice. Collisions in the asteroid belt occur at velocities measured in kilometers per second, typically 3 to 5 kilometers per second for objects in similar orbits. Higher for asteroids with eccentric or inclined trajectories that bring them crashing through the belt at angles. At these speeds, kinetic energy dominates over gravitational binding energy. Impacts don't accrete material together, but shatter it apart, fragmenting solid rock into debris clouds that eventually disperse along orbital paths, creating asteroid families that share common origins and similar compositions. The mathematics of collision probability requires calculating the cross-sectional area of all asteroids combined, then dividing by the total volume of space they occupy. The result, vanishingly small chance of any particular asteroid colliding with another in any given year. Current collision rates suggest that an average asteroid in the main belt will experience one catastrophic collision energetic enough to fragment it into smaller pieces every billion years. Smaller. Non-catastrophic collisions occur more frequently, perhaps every few million years, chipping fragments off surfaces, creating regolith, gradually eroding larger bodies into smaller ones. This erosion proceeds in one direction. Large asteroids break into smaller ones. Small asteroids break into even smaller fragments. Eventually, centimeter-sized particles get deflected by radiation pressure or swept up by planets, removed from the belt entirely. The size distribution of asteroids reflects this grinding process: many small objects, fewer large ones. The population following a power law where doubling the diameter reduces the number of objects by a factor of 8 or more only took 4 billion years to grind down. Yet some asteroids show evidence of gentle accretion rather than violent fragmentation. Rubble pile asteroids, as they're called, appear to be loose aggregations of fragments held together by gravity alone, with internal voids comprising 30 to 50% of total volume. These objects likely form through reaccumulation after a catastrophic collision, the fragments drifting close enough to each other that their mutual gravity pulled them back into a single body, loosely bound, porous, barely cohesive. Itokawa, a small near-Earth asteroid visited by Japan's Hayabusa spacecraft in 2005, exemplifies this structure. Shaped like an otter or a potato depending on viewing angle, measuring only 500 meters across. Itokawa appears to be two distinct lobes connected by a narrow neck. Its surface shows both smooth areas covered in fine regolith and rough areas strewn with boulders, suggesting the object formed from the collision of two separate asteroids that merged at low velocity. Their combined gravity insufficient to reshape the assemblage into a sphere. Internal density measurements confirm significant porosity. Itokawa contains nearly as much empty space as rock. Bennu. Another near-Earth asteroid examined extensively by NASA's OSIRIS-REx mission between 2018 and 2021 shows similar characteristics. Roughly 500 meters in diameter, spinning once every 4 hours. Its surface littered with boulders the size of buildings. When OSIRIS-REx touched down to collect samples in 2020, its collection arm sank unexpectedly deep into the surface. The asteroid's exterior proved less solid than anticipated, more like a ball pit filled with loosely packed fragments than coherent bedrock. The spacecraft had to fire thrusters to escape before sinking further, having collected far more sample material than planned simply because the surface offered so little resistance. These rubble pile structures create peculiar dynamics. Asteroids spinning faster than a certain rate, roughly one rotation every 2 hours, for objects Bennu's size would fly apart. their material escaping into space because centrifugal force exceeds gravitational binding. Most small asteroids rotate more slowly than this limit, suggesting that faster rotators did fly apart and no longer exist as intact objects. Natural selection operating on asteroid populations, eliminating configurations that can't maintain cohesion. Larger asteroids possess stronger gravity and can rotate faster without disrupting. Vesta spins once every 5 hours despite measuring over 500 kilometers in diameter. Its self-gravity sufficient to hold it together at this rate. Ceres rotates every 9 hours, its larger mass creating stronger binding. Both objects likely have differentiated interiors. Denser material settled toward the center during the brief period of internal heating provided by radioactive decay of aluminum-26 and other short-lived isotopes present during the solar system's formation. They are not rubble piles, but coherent bodies with distinct crusts, mantles, and cores, miniature planets that never quite achieved full planetary status. The energy released during collisions depends on velocity and mass. A 1-kilometer asteroid striking another at 5 kilometers per second releases energy equivalent to several thousand megatons of TNT, far exceeding the largest nuclear weapons ever tested, enough to vaporize both objects and create a debris cloud that takes thousands of years to disperse. The asteroid belt has witnessed millions of such collisions over its history, each one erasing whatever structures existed on the impacted bodies, resetting their surfaces to rubble, mixing their interiors, sometimes exposing mantles or cores that formed during differentiation billions of years earlier. Collision frequency has declined over time as the belt's population decreased. During the first billion years after planetary formation, impact rates ran perhaps 100 times higher than today. The belt contained more objects, orbiting at higher eccentricities, crossing paths more frequently. This early intense bombardment gradually cleared the most collision-prone orbits, removing objects that happened to be in resonances or on highly eccentric paths. The survivors occupy more stable orbits, less likely to intersect. Their future collisions spread across timescales longer than the solar system's remaining lifetime. Only took 1 billion years to calm down. 3 Atlas crosses through the belt entirely, its hyperbolic trajectory carrying it inward at 30 kilometers per second, faster than any asteroid orbits. If it were to strike an asteroid, probability essentially zero, given the vast empty spaces between objects, the impact energy would dwarf anything the belt has experienced in billions of years, but it strikes nothing, passes nothing closely, continues inward undisturbed. A visitor threading through the gravitational architecture without interaction, like a ghost passing through walls. The belt continues its slow, grinding, asteroid orbiting asteroid, velocities measured precisely by gravitational equations, collisions occurring on schedules measured in millions of years, patient mathematics, playing out in darkness, unchanged by the passage of interstellar visitors or the attention of distant observers. Only took 4 billion years to establish this rhythm. Perhaps it will continue another 4 billion more. Comets carry volatile materials that vaporize easily when heated, remaining frozen only at temperatures far below water's freezing point. Water ice dominates, comprising perhaps 70 to 80% of a typical comet's mass, frozen hard as granite at the temperatures prevailing in the outer solar system. Carbon dioxide ice makes up another 10 to 15%, along with smaller quantities of methane, ammonia, carbon monoxide, and various organic compounds, methane with its single carbon atom, ethane with 2, more complex chains containing dozens of carbon atoms linked together in ways that organic chemistry permits but rarely produces in cold interstellar clouds. These molecules formed in the solar nebula before planets existed, condensing from gas onto dust grains at temperatures cold enough that even carbon monoxide, which remains gaseous down to -200 Celsius, froze solid. The outer reaches of the protoplanetary disk, beyond Neptune's current orbit, provided these conditions. Ice accumulated on dust grains, grains stuck together, aggregates grew into larger bodies, eventually forming the icy planetesimals that make up the Oort cloud and Kuiper belt. Some of these bodies remained in place, orbiting at 40 to 50 astronomical units. Others were scattered by interactions with forming planets, ejected to greater distances, or sent plunging toward the inner solar system on long elliptical orbits that bring them back every few thousand years. When a comet approaches the Sun, crossing inside Jupiter's orbit, sunlight becomes intense enough to sublime surface ice. Water molecules escape into space, carrying dust particles with them, tiny grains of silicate and carbon that had been frozen in the ice for billions of years. These particles form the comet's dust tail, pushed outward by radiation pressure from sunlight, streaming behind the nucleus in a gentle curve that follows the comet's orbital path. The gas forms a separate tail, ionized by ultraviolet light from the sun, pushed straight outward by the solar wind at hundreds of kilometers per second. Two tails, pointing in slightly different directions, marking the comet's passage through the inner solar system. The coma, the cloud of gas surrounding the nucleus, can grow enormous. Some comets develop comas larger than Jupiter, extending millions of kilometers in all directions. Though this represents diffuse gas at densities approaching laboratory vacuum, the nucleus remains small, typically a few kilometers across, but its sublimating ice creates an atmosphere that temporarily makes it visible across the solar system. Comets brighten dramatically as they approach perihelion, sometimes becoming visible to the naked eye from Earth, occasionally achieving brightness rivaling Venus, or even the full moon for observers fortunate enough to witness a particularly active comet during close approach. Only took 4.5 billion years to be seen. The organic molecules carried by comets include amino acids, the building blocks of proteins, though not arranged in biologically useful configurations. Glycine, the simplest amino acid, has been detected in comet samples returned by the Stardust mission, which collected particles from Comet Wild 2's coma in 2004 and brought them to Earth for laboratory analysis. Other amino acids likely exist in cometary ice, frozen and inert, preserved since the solar system's formation. Whether these molecules contributed to the origin of life on Earth remains uncertain. Comets certainly delivered water and organic material during the late heavy bombardment 4 billion years ago, but whether this delivery included the specific molecules that sparked abiogenesis, or whether life originated from purely terrestrial chemistry, cannot be determined from current evidence. Sugars have also been detected, ribose among them, a 5-carbon sugar that forms the backbone of RNA, found in meteorites, likely present in comets, synthesized through chemical reactions in cold molecular clouds or on the surfaces of icy grains in the solar nebula. Ribose's presence in space suggests that the molecular components necessary for life chemistry are common, produced naturally wherever conditions permit, no biology required, just chemistry, obeying thermodynamics, creating complexity through random recombination over millions of years. 3I Atlas carries similar chemistry. Probably, its spectrum shows organic compounds without specifying their exact structures, carbon-hydrogen bonds detected through absorption features in infrared light, suggesting chains or rings of carbon atoms with hydrogen attached. Could be simple hydrocarbons like methane and ethane, could be more complex molecules, polycyclic aromatic hydrocarbons, or even amino acids, frozen in ice that has never been warm enough for liquid water to exist. Chemistry from another star system formed in another molecular cloud, similar to local chemistry because the laws of physics remain constant across the galaxy. The water in comets predates Earth's oceans. Isotopic ratios, the relative abundance of deuterium compared to hydrogen, vary between comets, but generally match ratios found in Earth's ocean water, suggesting a common origin in the solar nebula. Some comets show deuterium enrichment indicating formation at even colder temperatures, possibly in interstellar space before the solar system formed. Others match Earth's ratios precisely, supporting the hypothesis that cometary impacts delivered much of Earth's water during the period of heavy bombardment when the inner solar system was still being swept clean of debris. How much water did comets deliver? Estimates vary. Earth's oceans contain roughly 4 billion cubic kilometers of water, equivalent to about 1/4 Earth's total mass. Computer models of the late heavy bombardment suggest cometary impacts could have delivered several Earth oceans worth of water, most of which was lost to space through impacts energetic enough to blast atmosphere and water away. What remains the single ocean's worth currently present may represent only a fraction of what arrived. Only took a few 100 million years to fill the oceans. Cometary volatiles don't only include water, nitrogen. Present as ammonia ice or molecular nitrogen may have contributed to Earth's atmosphere, supplementing nitrogen released from volcanic outgassing. Carbon delivered by comets could have seeded early organic chemistry, providing raw materials for the complex carbon-based molecules that eventually led to life. Phosphorus, present in trace amounts in cometary dust, is essential for ATP and DNA, but relatively rare on Earth's surface. Cometary delivery may have provided enough phosphorus to enable biochemistry. Each comet represents a sample of the solar system's initial composition, a time capsule preserving volatiles that have remained frozen since before planets formed. Analysis of cometary chemistry provides constraints on conditions in the solar nebula temperatures, pressures, abundances of different elements that cannot be measured any other way. The Rosetta mission, which orbited comet 67P Churyumov-Gerasimenko for 2 years between 2014 and 2016, measured water isotopes, noble gas abundances, organic molecule concentrations, and dust compositions in unprecedented detail, revealing the comet's complex structure and varied chemistry. 3I Atlas will not be studied in such detail. Its brief passage through the inner solar system provides only weeks of observation time, and its interstellar velocity makes orbital rendezvous impossible with current technology. Spectroscopic observations from Earth must suffice measurements of light absorbed and reflected, revealing elemental abundances and molecular structures indirectly, leaving many questions unanswered. What exactly are those organic compounds? What isotopic ratios does its water show? Does it contain amino acids, sugars, or other prebiotic molecules? The answers depart with the comet, carried back into interstellar space, lost to observation as distance and dimness render it invisible. Only took a few months to pass through, an eternity to regret missing. The asteroid belt contains no planet because Jupiter prevented one from forming. But this explanation misleads, slightly suggests active prevention, deliberate disruption, as though Jupiter reached into the belt and scattered objects that were trying to coalesce. The reality involves more subtle dynamics. Jupiter simply existed where it existed, massive and gravitationally influential, and its presence changed the velocity distribution of objects in the adjacent region. Material that would have accreted gently at low relative velocities instead began colliding at speeds too high for sticking. The belt never started accumulating into a planet because the conditions necessary for accretion never developed in the first place. Computer simulations of planetary formation, run with varying initial conditions, show that, without Jupiter, The material in the asteroid belt would have formed a planet with perhaps twice Mars's mass within the first 10 million years of the solar system's existence. The planetesimals in this region had sufficient mass and density. Gravitational interactions would have caused them to merge gradually, building larger bodies that cleared their orbits, eventually resulting in a terrestrial planet orbiting at 2.5 astronomical units. This planet would have been rocky, differentiated, possibly retaining an atmosphere. It would have experienced volcanism during its early heating phase, developed a magnetic field if its core contained enough iron, perhaps even retained water on its surface if enough volatile-rich material was available. But Jupiter formed first, or nearly first, accreting gas from the solar nebula within a few million years of the Sun's ignition. Once Jupiter achieved its current mass, 318 Earth masses, mostly hydrogen and helium, its gravity dominated everything in the surrounding region. Objects orbiting near the belt experience perturbations that increase their orbital eccentricities, stretching circular orbits into ellipses. Eccentric orbits mean higher encounter velocities when objects cross paths. Higher velocities mean destructive rather than constructive collisions. The belt began grinding itself down instead of building up. This process was not instantaneous. Early in the solar system's history, the belt likely contained far more mass than it does today, perhaps 10 to 20 Earth masses of material, enough to form a substantial planet if accretion had proceeded normally. Over the first billion years, most of this material was removed. Objects in unstable resonances migrated inward or outward, eventually colliding with terrestrial planets or being ejected from the solar system entirely. Collisions fragmented larger bodies into smaller ones, creating debris that scattered along orbital paths. The belt lost 99% of its original mass, leaving only the sparse collection of asteroids present today. Only took 1 billion years to mostly disappear. The largest surviving object, Ceres, measures 940 kilometers in diameter, large enough to be classified as a dwarf planet under current definitions, but far smaller than any object classified as a full planet. Ceres achieved sufficient mass during its formation to undergo differentiation, its interior heating from radioactive decay until denser material sank toward the center. It developed a rocky core, a thick mantle of water ice mixed with hydrated minerals, and a thin crust. Dawn spacecraft observations between 2015 and 2018 revealed bright spots on Ceres' surface deposits of sodium carbonate, possibly erupted from subsurface brines, evidence of past or present geological activity driven by internal heat. Beneath Ceres' crust, evidence suggests a liquid water ocean may persist a global or regional layer of brine perhaps 40 kilometers below the surface, kept liquid by residual internal heat and salts that lower the freezing point. Gravity measurements made by Dawn indicate density variations consistent with a liquid layer, and the presence of ammonia-bearing minerals on the surface suggests the interior once contained significant quantities of liquid water. Ceres, alone among asteroid belt objects, may harbor an ocean, a miniature icy world hiding liquid water in darkness beneath its cratered crust. This ocean, if it exists, is not habitable by any conventional measure. Temperatures hover near freezing. Salinity likely exceeds ocean concentrations on Earth, and no energy source capable of driving metabolism seems available. No sunlight penetrates to those depths. No hydrothermal vents warm the water. Radioactive decay provides only minimal heat. Yet liquid water persists, perhaps, in an object that never became a planet, existing in the one place in the asteroid belt where gravity was strong enough to maintain differentiation and trap volatiles against billions of years of solar heating. Only took 4 billion years to possibly maintain an ocean. Vesta, the second largest asteroid at 525 kilometers in diameter, also differentiated early in its history, developing an iron core, a rocky mantle, and a basaltic crust. But Vesta was too small to retain water. Any ice present during formation was lost to space through impacts or sublimation, leaving only anhydrous minerals, rocks that never interacted with liquid water. Vesta resembles a planetary embryo, a body that began the process of becoming a terrestrial planet but stopped growing before achieving planet size. Its surface, mapped in detail by Dawn, shows volcanic features, impact basins, a complex geological history that ended billions of years ago when internal heat dissipated and volcanic activity ceased. The rest of the belt consists of smaller objects that never differentiated at all, rubble piles and solid bodies that remained too small for self-gravity to compress and heat their interiors. These objects retain their original composition, primitive material unchanged since the solar nebula collapsed. Carbonaceous chondrites, the most primitive meteorites found on Earth, originate from these bodies, carrying organic molecules, water-bearing minerals, and fine-grained dust that condense directly from nebula gas. They represent the building blocks from which planets form, preserved in the one region where planetary formation failed. Jupiter's migration through the early solar system, a gradual inward drift followed by outward movement, driven by interactions with the gas disk and with Saturn, may have disrupted the belt further, scattering objects that had achieved marginally stable orbits, clearing regions that might otherwise have contained more mass. The NICE model of solar system evolution, named for the French city where it was developed, proposes that the giant planets formed in a more compact configuration than today, then migrated outward to their current positions over tens of millions of years. This migration would have flung countless asteroids and comets throughout the solar system, creating the late heavy bombardment that scarred the Moon, Earth, and other terrestrial planets around 3.9 billion years ago. Whether the belt could have formed a planet in a solar system without Jupiter remains a thought experiment, no way to test it, no alternate universe to observe. In this universe, Jupiter exists, massive and disruptive, and the belt grinds slowly through its existence without coalescing, a collection of fragments marking the place where a planet might have been. The mathematics that prevented planetary formation continue operating, unchanged, maintaining the belt in its current configuration, ensuring that no accretion begins now, 4 billion years later, only took 4 billion years to conclusively not become a planet. The late heavy bombardment stands as one of the most consequential episodes in Earth's geological history. Though its existence remains debated, its causes uncertain, its timing questioned by researchers who note that evidence for a discrete bombardment event around 3.9 billion years ago may reflect sampling bias rather than actual spike in impact rates. Lunar samples collected during Apollo missions show clustering of impact melt ages around this date, rocks melted by asteroid and comet strikes, subsequently crystallized, their radiometric clocks reset to mark the moment of impact. Hundreds of samples, most dating to between 3.8 and 4.1 billion years ago, suggesting intense bombardment during this narrow window. But the Moon preserves only surface samples from a few locations, and these locations may not represent the Moon's entire impact history. Perhaps impacts occurred continuously from the Moon's formation 4.5 billion years ago until 3 billion years ago, with the 3.9 billion year cluster reflecting nothing more than the age of the most recently excavated basin, Imbrium, whose ejecta blankets much of the near side. Perhaps the late heavy bombardment is an artifact of incomplete sampling, a story told by a few dozen rocks that happen to date to the same era because they all came from the same impact event. Or perhaps it was real, a genuine spike in bombardment caused by dynamical instability among the giant planets. Migration that sent Jupiter and Saturn into resonant orbits that gravitationally perturbed the remaining planetesimals in the outer solar system, flinging them inward toward the terrestrial planets. The NICE model proposes exactly this scenario, calculating that Jupiter's migration would have destabilized the outer asteroid belt and scattered objects from the Kuiper belt throughout the inner solar system. For a few 100 million years, impact rates would have increased dramatically, then declined as the scattered population was depleted through collisions or ejections. Evidence beyond the Moon supports heightened bombardment during this period. Ancient Martian terrains show heavy cratering consistent with late, heavy bombardment timing. The oldest terrestrial rocks, scarce because plate tectonics recycles Earth's crust, include shocked minerals and spheroidal layers indicating large impacts around 3.9 billion years ago. Asteroids themselves show evidence of collisional disruption during this era, with many asteroid families dating their formation to between 3.8 and 1 billion years ago based on cratering statistics and dynamical modeling, only took a few 100 million years to reshape the inner solar system. Impact rates during the bombardment may have exceeded current rates by a factor of 100 or more. Earth, with its larger cross-sectional area and stronger gravity, would have received proportionally more impacts than the Moon. Estimates suggest Earth experienced dozens of basin-forming impacts, objects 10 kilometers across or larger, releasing energies equivalent to billions of megatons, vaporizing oceans locally, ejecting enough debris to temporarily darken the sky. Smaller impacts would have occurred far more frequently, thousands of kilometer-sized objects, millions of 100-meter objects, creating craters across the entire surface. Whether these impacts sterilized Earth or delivered the ingredients for life remains contentious. Large impacts release enough energy to vaporize oceans and melt the crust, creating conditions hostile to any biology that might have existed. But impacts also deliver organic compounds, water, and volatiles, the raw materials necessary for life chemistry. Some researchers propose that life originated multiple times during the bombardment, sterilized by large impacts, re-originating afterward using freshly delivered organic material. Others suggest life persisted through the bombardment in deep-sea hydrothermal vents where temperatures remained stable despite surface chaos. The oldest evidence for life on Earth, stromatolites, layered structures formed by microbial mats, dates to approximately 3.5 billion years ago, just after the proposed end of the late heavy bombardment. Earlier, evidence exists but remains controversial. Carbon isotope ratios in 3.8 billion-year-old rocks from Greenland suggest biological activity, but abiotic processes can produce similar isotopic signatures, and the rocks have been metamorphosed enough that original structures are difficult to interpret. Whether life existed before the bombardment, whether it survived through it, or whether it originated immediately afterward cannot be determined from current evidence. Impact rates declined dramatically after the bombardment ended. The scattered population of planetesimals was depleted. Remaining objects settled into more stable orbits. The inner solar system transitioned from chaotic to relatively calm, with impacts becoming rare rather than constant. Current impact rates one civilization-threatening impact every few million years. One city-destroying impact every few thousand years represent the tail end of this decline. The final cleanup of debris from planetary formation only took 4 billion years to mostly calm down. Earth's geological record preserves only a handful of confirmed impact craters older than 1 billion years. Plate tectonics and erosion have erased the rest. The Moon, lacking these resurfacing processes, maintains a cratered surface recording impacts across its entire history. By counting craters of different sizes and using radiometric dating of impact melts, researchers can reconstruct impact flux over time. The resulting curve shows exponential decline from formation to present, steep early on, gradually flattening, approaching but never quite reaching zero. Impacts continue, will continue, their frequency governed by the population of objects in planet-crossing orbits, a population that depletes slowly as objects collide with planets or are ejected from the solar system entirely. The asteroid belt contributed many impactors during the bombardment. Probably, objects in unstable resonances migrated inward, crossing Mars's orbit, eventually encountering Earth or Venus. Comets from the Kuiper belt and Oort cloud added to the bombardment, their highly elliptical orbits bringing them through the inner solar system at high velocities, impacting with energies greater than typical asteroid strikes. Both populations contributed to reshaping the inner planet's surfaces, delivering volatiles, possibly seeding Earth with organic compounds that later participated in the origin of life. Today's belt is the depleted remnant of that earlier population. Most of the mass that once orbited between Mars and Jupiter is gone, collided with planets, ejected to interstellar space, or scattered into the Kuiper belt or Oort cloud by Jupiter's gravity. What remains orbits stably, its resonances cleared of objects, its collective mass insufficient to form a planet even if Jupiter's perturbations ceased. The bombardment will not repeat. The solar system has finished its violent youth and entered a long middle age, impacts becoming rare, surfaces stabilizing, the chaos of formation fading into deep time. Only took 1 billion years to transition from catastrophic to calm. 3I Atlas passes through a solar system vastly quieter than the one that existed 4 billion years ago. The inner system is swept clean, the asteroid belt sparse, the giant planets settled into stable orbits. No late heavy bombardment occurs. No migration disrupts the outer system, just orbital mechanics, proceeding predictably. Objects moving along paths determined billions of years ago, disturbed only occasionally by rare collisions or gravitational perturbations too subtle to notice without decades of precise observation. Ceres drifts through the asteroid belt at 227 astronomical units from the Sun, completing one orbit every 6 Earth years, its surface temperature hovering around -100 Celsius in sunlight, dropping to -150 Celsius in shadow. The surface appears gray-brown in visible light, heavily cratered. Ancient. Some regions date to Ceres's formation 4.5 billion years ago, their crater densities indicating surfaces that have remained largely unchanged since the solar system's youth. Other regions show fewer craters, suggesting more recent resurfacing, perhaps through cryovolcanism or subsurface brine reaching the surface and refreezing into smooth plains. The bright spots that drew initial attention when dawn approached in 2015 turned out to be deposits of sodium carbonate mixed with smaller amounts of ammonium chloride and ammonium carbonate salts precipitated from brines that welled up through fractures in the crust. The brightest concentration, located in a crater, covers an area roughly 10 kilometers across, reflecting 60% of incident sunlight compared to 3 to 4% for typical surface material. The salts likely originated from a subsurface reservoir of liquid brine, driven upward by pressure from below or by impact fracturing that created pathways to the surface. Spectroscopic observations revealed water ice exposed on Ceres's surface in permanently shadowed craters near the poles, similar to water ice deposits found on the Moon and Mercury. These deposits remain stable because shadowed crater floors never receive direct sunlight, maintaining temperatures cold enough that sublimation proceeds immeasurably slowly. Water molecules remain frozen for billions of years, preserved in darkness, untouched by solar heating. The ice may be primordial, dating to Ceres' formation, or it may be relatively recent, delivered by comet impacts within the last few million years. Dawn's gravity measurements, conducted by precisely tracking the spacecraft's motion as it orbited Ceres, revealed density variations consistent with a differentiated interior. The data suggest a rocky core roughly 200 kilometers in radius, overlain by a water ice mantle perhaps 100 kilometers thick, topped by a crust of hydrated minerals and salts. Total water content may exceed 25% of Ceres' mass, more water than all of Earth's fresh water combined, locked in ice and minerals in a body less than 1,000 kilometers across. Only took 4 billion years to store an ocean's worth of water in frozen form. The question of whether liquid water exists beneath Ceres' surface remains unresolved. Gravity data indicates possible density variations consistent with a regional or global liquid layer, perhaps 40 to 100 kilometers below the surface. The presence of salts on the surface suggests past or recent liquid brine activity. Ammonia compounds detected by Dawn's spectrometer should have been destroyed by cosmic ray bombardment over geological timescales, their presence implying recent emplacement from the interior. All evidence points towards subsurface liquid, but none proves it definitively. If such an ocean exists, it would represent the innermost ocean in the solar system, closer to the Sun than Jupiter's moons Europa, Ganymede, and Callisto, closer even than Saturn's moon Enceladus, all of which likely harbor subsurface oceans beneath icy crusts. But Ceres' ocean, if present, differs from those distant moons. No tidal heating warms Ceres, it orbits the Sun alone. Not locked in gravitational resonances with massive planets, its internal heat comes only from residual warmth from formation and decay of radioactive isotopes, primarily potassium-40, which has a half-life of 1.25 billion years and continues producing small amounts of heat even now. Whether this heat suffices to maintain liquid water depends on several factors: the concentration of salts, which lower water's freezing point, the thickness of the insulating crust, which traps heat, the amount of remaining radioactive material in the core, and the presence of any geochemical reactions that might produce additional heat. Models suggest that liquid water could persist if salt concentrations reach 25% or higher, a brine so salty it would taste undrinkable, but liquid nonetheless, possibly extending across much of Ceres' interior between the rocky core and the icy mantle. No life exists in this hypothetical ocean, almost certainly. No energy source capable of sustaining metabolism has been identified. No sunlight penetrates. No tidal heating warms the water. Radioactive decay produces only minimal heat, insufficient for driving convection or chemical cycling. Organic compounds may exist, delivered during Ceres' formation from carbonaceous material in the solar nebula, but without energy to drive reactions, they remain inert. The ocean, if it exists, sits cold and still, slowly freezing from above as internal heat dissipates, eventually destined to become solid ice throughout as the last warmth radiates away into space. Only took 4 billion years, might take another 4 billion to freeze completely. Ceres' geology appears inactive by terrestrial standards, but shows evidence of recent activity by asteroid standards. Ahuna Mons, a solitary mountain rising 4 kilometers above the surrounding plains, shows morphological features consistent with a cryovolcanic dome, a structure formed by viscous icy material extruded from below, piling up into a mountain because Ceres' weak gravity cannot flatten it quickly. Age estimates based on crater density suggest Ahuna Mons formed within the last few 100 million years, geologically recent for an asteroid belt object. Whether it represents the most recent of many such features or a unique event remains uncertain. The mountain's existence implies that Sirius's interior retained enough heat to mobilize material within relatively recent geological time. Cryovolcanism requires temperatures warm enough to soften ice mixed with salts and clays, creating a slurry that can flow upward through fractures under pressure. The energy source for this activity might be residual differentiation, denser materials sinking through the mantle, converting gravitational potential energy to heat, or it might be radiogenic heating from long-lived isotopes, or both. Regardless of mechanism, Ahuna Mons stands as evidence that Ceres was not geologically dead even a few 100 million years ago. Whether other dwarf planets in the asteroid belt harbor similar features remains unknown. Vesta shows no evidence of cryovolcanism. Its composition lacks sufficient water for ice-based geology. Pallas, the third largest asteroid at 5 or 12 kilometers diameter, has not been visited by spacecraft, though spectroscopic observations suggest a composition similar to carbonaceous chondrites, implying water-bearing minerals. Hygeia, fourth largest at 434 kilometers, also remains unvisited and poorly characterized. Perhaps they, too, differentiated and retain subsurface ice. Perhaps they, too, harbor or once harbored liquid water. The asteroid belt keeps its secrets, reveals them only slowly, through patient observation and rare spacecraft visits. Ceres orbits onward, rotating once every 9 hours, its surface unchanging on human timescales, its interior slowly cooling, its hypothetical ocean slowly freezing, its isolated existence continuing as it has for billions of years. The largest object in the asteroid belt, alone in its size class. A dwarf planet that never became a planet, holding more water than appears on Earth's surface, hiding it beneath a cratered crust in darkness and silence. Only took 4 billion years to possibly maintain liquid water, only took until 2015 for anyone to visit. Carbonaceous chondrites arrive on Earth regularly, falling through the atmosphere as meteorites, collected in Antarctica's blue ice fields or the Sahara's empty expanses where dark stones stand out against light backgrounds. These meteorites contain the most primitive material available for study dust and pebbles that accreted in the solar nebula before planets formed, compressed into larger bodies but never heated enough to melt, never differentiated into cores and mantles, preserving their original composition across 4.567 billion years. The age is known precisely, measured through radioactive decay of uranium and lead in mineral grains called calcium-aluminum inclusions, the first solids to condense from nebular gas. The meteorites feel light for their size, their low density reflecting high porosity void spaces comprising 10 to 30% of total volume, gaps between mineral grains never filled, preserved since accretion. When broken open, they reveal a matrix of fine-grained clay minerals mixed with larger inclusions chondrules, millimeter-sized spheres of once molten silicate that formed through flash heating in the solar nebula, CAIs, white calcium-aluminum-rich inclusions that condensed at temperatures above 1300 Celsius, metal grains, tiny flecks of iron-nickel alloy, and organic matter, complex carbon-bearing compounds that give some carbonaceous chondrites their dark color and distinctive smell, sulfurous, organic, like nothing terrestrial. The organic matter interests astrobiologists particularly. Amino acids exist in these meteorites, more than 70 different types identified in the Murchison meteorite alone, which fell in Australia in 1969 and has been analyzed extensively in laboratories worldwide. Most of these amino acids do not occur in terrestrial biology. Some exist in equal mixtures of left-handed and right-handed forms, unlike biological amino acids, which are exclusively left-handed. This race-mech mixture, equal proportions of both chiralities, indicates non-biological synthesis, formation through chemical reactions that show no preference for one-handedness over the other. Yet the amino acids are real, complex, structurally identical to those used in proteins, differing only in their distribution of chiralities. They formed somewhere in the solar nebula or in the parent asteroid's interior through reactions between water, ammonia, and simple organic compounds, catalyzed by minerals, proceeding over millions of years at temperatures barely above freezing. Organic chemistry operating without life, creating biological building blocks through purely abiotic processes, demonstrating that the molecules necessary for life arise naturally wherever appropriate conditions exist. Only took a few million years to synthesize amino acids without biology. Sugars also exist in carbonaceous chondrites. Ribose, the 5-carbon sugar that forms RNA's backbone, has been identified along with other sugars containing 3 to 6 carbon atoms. These molecules are fragile, they degrade easily in water, react readily with other compounds, exist in meteorites only in trace quantities measured in parts per billion, but they exist, synthesized through foremost reaction pathways where formaldehyde molecules link together in the presence of mineral catalysts, building larger sugar molecules step by step. The same chemistry could have operated on early Earth, in tidal pools or hydrothermal settings, creating sugars from simple precursors. Water-bearing minerals pervade carbonaceous chondrites phyllosilicates, clays that form when anhydrous minerals react with liquid water, incorporating water molecules into their crystal structures. The presence of these clays indicates that liquid water existed in the meteorite parent bodies, maintained at temperatures between 0 and 100 Celsius for thousands or millions of years, while aqueous alteration proceeded. The asteroids that produced these meteorites were not always frozen. They contained ice that melted due to heat from radioactive decay, creating internal reservoirs of liquid water where minerals dissolved, recrystallized, and reacted with organic compounds. The parent bodies were probably 50 to 100 kilometers in diameter, large enough that internal heat from aluminum-26 decay a short-lived radioactive isotope present in the early solar system with a half-life of only 717,000 years warmed their interiors above freezing. Liquid water percolated through the rock, forming veins and pockets, perhaps creating connected aquifer systems where water flowed slowly through porous material. These subsurface oceans existed briefly. Geologically speaking, aluminum-26 decayed completely within a few million years. The heat ceased, temperatures dropped, water refroze, but for that brief interval, liquid water and organic compounds coexisted in darkness inside small asteroids drifting through the early solar system. Whether any biochemistry began in these environments remains unknown. The conditions seem marginally favorable: liquid water, organic compounds, mineral catalysts, energy from radioactive decay. But the timescales seem too short. Life requires millions or billions of years to originate through random chemistry, and these asteroidal aquifers existed for only a few million years before freezing. Perhaps prebiotic chemistry advanced partway toward life, creating more complex molecules, establishing reaction networks that approached but never achieved self-replication. Perhaps the asteroids simply processed organic material without creating anything novel, rearranging molecules without generating complexity. The carbonaceous chondrites that fall to Earth now sample these ancient aquifer systems, preserved as frozen snapshots of early solar system chemistry. The amino acids, sugars, clays, and organic matter they contain represent the chemical environment that existed in small bodies 4.5 billion years ago. Some of these bodies later collided with Earth during the late heavy bombardment, delivering their organic cargo to a planet where liquid water existed on the surface, where energy from sunlight and hydrothermal vents sustained chemical reactions, where timescales extended to billions of years, conditions far more favorable for the origin of life than briefly melted asteroid interiors. Current understanding suggests Earth's organic compounds originated from multiple sources: synthesis in the atmosphere through lightning-driven reactions, production in hydrothermal vents through mineral-catalyzed chemistry, delivery from comets and asteroids during bombardment, and possibly synthesis on dust grains in the solar nebula before Earth accreted. Carbonaceous asteroids contributed to this inventory, but probably didn't dominate it. Their main contribution may have been water rather than organics. Isotopic studies suggest much of Earth's water matches carbonaceous chondrite compositions, supporting the hypothesis that water-rich asteroids delivered significant fractions of Earth's oceans. Only took a few 100 million years to deliver an ocean. Samples of carbonaceous asteroids have been returned to Earth by spacecraft. Japan's Hayabusa 2 mission collected samples from asteroid Ryugu in 2019, returning them to Earth in 2020. NASA's OSIRIS-REx mission collected samples from asteroid Bennu in 2020, returning them in 2023. Laboratory analysis of these samples revealed amino acids, organic compounds, water-bearing minerals, and complex carbon chemistry, confirming and extending what had been inferred from meteorites, which might have been contaminated by terrestrial organics after landing. The spacecraft samples arrived pristine, sealed in containers never exposed to Earth's atmosphere, providing unambiguous evidence for extraterrestrial organic chemistry. The asteroids continue their patient orbits, carrying their ancient chemistry through space, occasionally colliding with each other or fragmenting into smaller pieces that eventually migrate inward and fall to Earth. The solar system produces a steady rain of organic material onto all inner planets, delivery continuing at reduced rates compared to the bombardment era, but never ceasing entirely. Mars receives this material. Venus receives it, though high surface temperatures destroy organic compounds quickly. Even the Moon receives occasional carbonaceous meteorite impacts, though without an atmosphere to slow them. Most impact energy vaporizes incoming material rather than delivering it intact. Only Earth, with its thick atmosphere and abundant surface water, can receive and preserve delivered organics in forms accessible to potential biochemistry. Surveillance systems track near-Earth objects continuously. Automated telescopes scanning the sky each night, detecting faint points of light moving against the background stars, calculating orbits, assessing collision probabilities. The Catalina Sky Survey, PAN-STARRS, ATLAS acronyms representing telescope networks scattered across mountaintops in Arizona, Hawaii, and elsewhere, collectively discovering hundreds of new asteroids each month. Most pose no threat, their orbits carrying them nowhere near Earth's path, but each one gets catalogued, monitored, its trajectory refined through repeated observations until uncertainty shrinks to acceptable levels. Near-Earth objects are defined as asteroids or comets with perihelion distances less than 1.3 astronomical units, objects whose orbits bring them within 195 million kilometers of the Sun, close enough that they cross or approach Earth's orbital path. The population includes roughly 25,000 known objects larger than 140 meters in diameter, though completeness estimates suggest the true population exceeds 40,000. Smaller objects exist in far greater numbers, perhaps 1 million objects larger than 30 meters, tens of millions larger than 10 meters. Detection bias favors large objects and those that pass particularly close to Earth. Small, distant objects remain mostly invisible. The size threshold of 140 meters is not arbitrary. It represents approximately the smallest object capable of penetrating Earth's atmosphere without completely fragmenting, retaining enough mass to create a crater and cause regional destruction. Smaller objects typically explode at high altitude, dissipating their energy in the atmosphere, producing brilliant fireballs but limited ground damage. The Chelyabinsk meteor in 2013 measured roughly 20 meters across, exploded at 30 kilometers altitude, released energy equivalent to 500 kilotons of TNT, shattered windows across a wide area, injured 1,500 people with flying glass, but created no crater. Larger objects reach the surface intact or nearly intact, their impacts excavating craters and causing destruction proportional to their size. Impact energy scales with the cube of diameter. Doubling an asteroid's size increases impact energy eightfold. A 140-meter asteroid releases roughly 300 megatons on impact, enough to devastate an area the size of a large city. A 1-kilometer asteroid releases 100,000 megatons, enough to cause global climate disruption through dust ejected into the stratosphere, potentially triggering crop failures and famine. A 10-kilometer asteroid, the size that ended the Cretaceous period 66 million years ago, releases 100 million megatons, sufficient to cause mass extinction, reshaping Earth's biosphere for millions of years afterward. Only took one impact to end the age of dinosaurs. Current surveys have identified approximately 95% of near-Earth objects larger than 1 kilometer. None of these objects will impact Earth within the next century based on orbital calculations, though uncertainties increase for predictions beyond 100 years due to accumulated errors in trajectory measurements and unpredictable gravitational perturbations from other planets. The remaining 5% of undiscovered kilometer-sized objects exist, statistically speaking, but their orbits apparently keep them far from Earth or their brightness remains below detection thresholds. Eventually, they will be found, observed, catalogued, their threat assessed or dismissed. Smaller objects remain poorly surveyed. Perhaps 30% of 140-meter objects have been discovered, leaving thousands undetected, some of which orbit in paths that will eventually intersect Earth's. These objects drift through space invisibly, too small to reflect much sunlight, too distant to show up in current surveys, slowly migrating through orbital resonances or being perturbed by close encounters with planets. They will be discovered eventually, perhaps decades before impact, perhaps only months, depending on their orbital characteristics and when their paths happen to carry them through surveyed regions of sky. The probability of impact follows Poisson statistics events occurring randomly in time with some average rate. For 1-kilometer objects, impact probability is roughly 1 per 500,000 years. For 140-meter objects, roughly 1 per 10,000 years. For Chelyabinsk-sized objects, roughly 1 per century. These are average rates, not guarantees 3 centuries might pass without impact, then 2 impacts might occur within a decade. The statistics provide no comfort at individual timescales, only at civilizational ones. Only took 66 million years between dinosaur-ending impact and present, statistically overdue for another large impact by Poisson statistics. Though such reasoning commits the gambler's fallacy, detection provides options. If an asteroid is discovered decades before impact, interventions become possible. Gravitational tractors that slowly alter trajectories through sustained low thrust, kinetic impactors that strike the asteroid to change its velocity, or more exotic proposals involving painting the asteroid's surface to change solar radiation pressure effects, altering its orbit through subtle but cumulative forces. If discovery occurs only months before impact, options narrow considerably. Evacuation becomes the only response, moving populations away from predicted impact zones, preparing for regional or global consequences depending on the object's size, NASA's DART mission in 2022 demonstrated kinetic impactor technology successfully, striking the small moon. Dimorphos orbiting the asteroid Didymos at 6.6 kilometers per second, changing Dimorphos's orbital period by 33 minutes, far more than the minimum 5-minute change required to declare success. The impact was detected through ground-based observations of Didymos's brightness variations, which change as Dimorphos orbits around it. Kinetic impactors work, at least for small objects, given sufficient lead time and favorable circumstances. Larger objects would require multiple impactors or more energetic interventions. What remains undetected vastly exceeds what has been found. Millions of objects larger than 10 meters orbit through the inner solar system, most of them invisible, their trajectories unknown, their positions uncalculated. They drift through space in silence, occasionally passing close to Earth without being noticed, sometimes impacting without warning. Most land in oceans or uninhabited regions, their impacts going unrecorded except by infrasound monitoring stations that detect atmospheric shock waves from explosions. A few impact-populated areas, like Chelyabinsk, creating dramatic fireballs and minor damage. Very rarely, larger objects impact, creating catastrophe. The asteroid belt contributes to the near-Earth object population continuously, though slowly. Objects in resonances migrate inward over millions of years, their orbits becoming increasingly eccentric until they cross Mars's path. Then Earth's. Some collide with planets. Some are ejected from the inner solar system entirely through close encounters with Jupiter. The belt slowly bleeds mass into the inner system at rates too slow to measure directly but calculable through statistical modeling. Only took 4 billion years to partially clear the belt into near-Earth space. 3I Atlas will not join this population. Its velocity is too high, its trajectory hyperbolic. Departing the solar system permanently after perihelion, it poses no threat to Earth, passes no planet closely, intersects no orbit of significance. Surveys detected it, calculated its trajectory, determined it safe, continue monitoring it as it departs, not because it threatens anything, but because interstellar objects are rare and worthy of study. The infrastructure built to detect dangerous asteroids functions equally well for detecting harmless ones, cataloging everything that moves, threatening or not. The watch continues. Night after night. Telescopes slewing across the sky, cameras recording, computers analyzing, orbits calculating. Approximately 30 asteroids discovered per night on average, most of them tiny, distant, safe. Perhaps 1 in 10,000 warrants closer attention. Its orbit passing near enough to Earth that follow-up observations become necessary to reduce uncertainty. Most of these closer observations confirm safety. Occasionally, they confirm threat, though no imminent impacts have been confirmed yet. Only approaches close enough to cause concern before refined calculations demonstrate missed distances measured in lunar distances or greater. Only took until the 21st century to begin systematically watching. The watching continues. Statistical silence offers comfort of a peculiar kind. The knowledge that catastrophic impacts occur so rarely that entire civilizations can rise and fall without experiencing one. That recorded human history spans only 5,000 years, while civilization-ending impacts average 1 per few million years, that the probability of dying in an asteroid impact remains orders of magnitude lower than dying in an automobile accident or from preventable disease. The mathematics reassures multiply impact probability by potential casualties, sum across all possible impact scenarios, and the annual risk to any individual human becomes vanishingly small, negligible compared to mundane hazards encountered daily. Yet, the same mathematics that dismisses individual risk affirms civilizational risk. Over timescales of thousands or millions of years, large impacts become not improbable, but inevitable. The asteroid belt contains enough material in planet-crossing orbits. The near-Earth object population replenishes itself through ongoing migration from the belt, and orbital mechanics ensure that eventually, some object will arrive at Earth's location at precisely the moment Earth occupies that location. The timing remains uncertain, but the occurrence does not. An impact will happen. Perhaps in 1,000 years, perhaps in 1 million, but eventually, necessarily, mathematically certain, given sufficient time. The Chicxulub impact 66 million years ago released energy equivalent to 10 billion Hiroshima bombs, excavated a crater 180 kilometers in diameter, ejected enough material into the atmosphere to darken skies worldwide for months or years, ignited global wildfires through thermal radiation from re-entering ejecta, triggered mega tsunamis that swept across coastlines, and acidified oceans through dissolution of sulfur-bearing minerals vaporized from the impact site. 3/4 of plant and animal species went extinct, including all non-avian dinosaurs, marine reptiles, pterosaurs, and ammonites. The extinction took thousands of years to fully play out, but the trigger was instant: a 10-kilometer asteroid arriving from space at 20 kilometers per second, converting kinetic energy to heat and shock in milliseconds. Only took milliseconds to end an era. Smaller impacts occur more frequently, but cause less comprehensive destruction. The Tunguska event in 1908 involved an object perhaps 50 to 100 meters across, exploding at 5 to 10 kilometers altitude above Siberia, flattening 2,000 square kilometers of forest, but causing no confirmed human fatalities due to the region's sparse population. Had the same explosion occurred above a city, casualties would have numbered in the hundreds of thousands. The timing was fortunate, the location remote, the damage limited to trees that regrew within decades. Only took one atmospheric explosion to flatten a forest. Barringer Crater in Arizona, formed approximately 50,000 years ago, marks the impact of a 50-meter iron asteroid that exploded on contact with the ground, excavating a crater 1.2 kilometers across and 170 meters deep. The impact occurred during the Pleistocene, when megafauna roamed North America and humans had recently arrived from Asia. No evidence suggests humans witnessed the impact, though they certainly encountered the crater afterward, a perfect bowl in the desert, its rim rising above the surrounding plain, its floor flat and features less, until erosion began filling it with sediment. The crater remains today, visited by tourists, studied by planetary scientists, a reminder that impacts occur not just in deep time, but within time scales relevant to human memory. Ocean impacts. Statistically more likely than land impacts due to oceans covering 70% of Earth's surface, produce different consequences. The asteroid vaporizes a cylinder of water, the ocean rushes in to fill the void, mega tsunamis radiate outward in all directions. Coastal regions experience wave heights measured in tens or hundreds of meters depending on the impact energy and distance from shore. The Eltanin impact, approximately 5 million years ago, involved a 1 to 4 kilometer asteroid striking the Pacific Ocean near South America, producing tsunami deposits found in Chile and Antarctica. No mass extinction resulted. Ocean impacts lack the dust injection and global climate effects of land impacts, but regional devastation would have been severe for any coastal ecosystems or, hypothetically, any civilizations that might have existed. Current impact monitoring focuses primarily on atmospheric and land impacts because these can be predicted through orbital tracking. Ocean impacts receive less attention, though they occur more frequently. because predicting where an asteroid will impact requires knowing its orbit precisely. And once the orbit is known, intervention becomes possible to deflect it away from Earth entirely. The goal is not to predict whether an impact will occur in the ocean or on land, but to prevent impacts altogether through early detection and deflection. Only took until the 21st century to consider prevention. The comfort of statistical silence relies on incomplete monitoring. If tomorrow a survey discovered a 500-meter asteroid on a collision course with Earth, arriving in 3 years, the silence would end. Evacuation of predicted impact zones would begin. Preparations for global climate disruption would commence. Attempts at deflection might be mounted. Though 3 years provides limited time for intervention, society would face the reality that statistics describe populations, not instances, and that low probability events eventually occur if enough trials run. No such object has been discovered yet. Current surveys suggest none exists among the known near-Earth object population, but the unknown population remains substantial, perhaps 70% of 140-meter objects, 95% of 30-meter objects. Essentially, all 10-meter objects remain undetected. These objects drift through space invisibly, their orbits calculated by no one, their trajectories unknown, their future intersections with Earth unpredicted. Most will never impact Earth. Some will. The timing remains uncertain. The same dynamics that created the asteroid belt and scattered near-Earth objects throughout the inner solar system continue operating unchanged, slowly grinding the belt through collisions and resonances, migrating fragments inward, maintaining a steady population of planet-crossing objects that depletes through collisions and ejections but replenishes through ongoing migration. The rate has declined over billions of years as the belt's mass decreased, but the process continues, will continue for billions more years until the Sun expands into a red giant and engulfs the inner planets entirely. Only took 4 billion years to partially clear the belt. Might take another 4 billion to mostly clear it. Earth orbits through this environment, sweeping up material continuously, micrometeorites by the ton daily. Boulder-sized objects occasionally, house-sized objects rarely, mountain-sized objects very rarely. The planet's cross-sectional area is large by human standards, but tiny compared to the volume of space it traverses. Most near-Earth objects pass harmlessly by, missing Earth by millions or tens of millions of kilometers. Their closest approaches going unnoticed except by automated surveys that detect and catalog everything. Occasionally, very occasionally, one arrives at the wrong place at the wrong time, and the silence breaks. The statistical comfort remains valid. Mathematically, individual risk is negligible. The probability of any specific person dying in an asteroid impact approaches 0, but civilizational risk accumulates over time, and humanity now occupies enough of Earth's surface, concentrates enough population in coastal cities, depends enough on interconnected systems vulnerable to disruption, that even a regional impact would cause global consequences. The Tunguska event over Manhattan would kill millions. A Chicxulub-scale impact anywhere would threaten civilization itself. The mathematics that dismisses individual risk affirms collective vulnerability. Only took until modern times to realize statistical comfort provides limited actual comfort. Jupiter orbits the Sun at 5.2 astronomical units, completing one revolution every 11.8 Earth years. Its mass so enormous, 318 times. Earth's 2.5 times all other planets combined, that the Sun and Jupiter orbit a common center of mass located outside the Sun's surface. The planet does not orbit the Sun so much as the two bodies orbit each other. a binary system where one partner outweighs the other by a factor of 1,000, but both respond to gravitational attraction. This massive presence shapes the entire solar system's architecture, determining which orbits remain stable and which decay, sculpting the asteroid belt through resonances, deflecting comets inward or outward depending on geometry. The planet's role as shield or threat depends on perspective and time scale. In the short term, decades to centuries, Jupiter deflects most long-period comets arriving from the Oort cloud, its gravity bending their trajectories, often flinging them back outward or into the outer solar system before they reach the inner planets. Computer simulations of solar system dynamics suggest that without Jupiter, Earth would experience perhaps 10 times more cometary impacts, the increased bombardment rate creating significantly more hazardous conditions for life. From this perspective, Jupiter serves as guardian, its gravity sweeping the outer solar system clear of incoming threats, protecting the terrestrial planets through sheer gravitational dominance. Only took 4 billion years to appreciate the protection, but Jupiter also perturbs objects into planet-crossing orbits. The Kirkwood gaps in the asteroid belt mark locations where Jupiter's resonances gradually increase orbital eccentricities, transforming stable main belt asteroids into near-Earth objects over millions of years. Objects that would otherwise orbit harmlessly between Mars and Jupiter find their paths stretched into ellipses that intersect Earth's orbit, creating collision opportunities that would not exist if Jupiter were absent or less massive. The same gravitational influence that shields against comets simultaneously supplies asteroids to the inner solar system, maintaining the near-Earth object population that threatens Earth. The late heavy bombardment, if it occurred as the NICE model proposes, resulted directly from Jupiter's migration. As Jupiter moved through the early solar system, its resonances swept through regions occupied by asteroids and comets, destabilizing their orbits, scattering them throughout the inner solar system in a pulse of impacts lasting tens of millions of years. The bombardment that may have delayed or destroyed early life on Earth, that certainly resurfaced the Moon and Mars, that reset geological clocks on all terrestrial planets, originated from Jupiter's gravitational influence, a delayed consequence of planetary migration driven by interactions with the dissipating gas disk from which planets formed. Whether Jupiter's net effect on Earth proves beneficial or harmful cannot be calculated definitively. The planet reduces long-period comet impacts but increases asteroid impacts. It shortened the late heavy bombardment but may have caused it in the first place. It prevents asteroid belt accretion, maintaining a reservoir of material that continuously feeds the near-Earth object population, ensuring that impacts continue at reduced but non-zero rates indefinitely. Statistical models that simulate solar systems with varying Jupiter masses find complex, non-monotonic relationships between Jupiter's mass and Earth's impact rate. Increasing Jupiter's mass sometimes increases impacts, sometimes decreases them, depending on subtle dynamical effects that compound over millions of years. Jupiter's Trojan asteroids, thousands of objects clustered 60 degrees ahead of and behind Jupiter in its orbit, demonstrate the planet's ability to trap objects in stable configurations. These asteroids remain permanently bound to Jupiter's orbital motion, held in place by the gravitational balance between Sun and planet, neither escaping to interplanetary space nor falling into Jupiter itself. They represent captured populations, perhaps originally from the Kuiper belt, swept inward during Jupiter's migration and trapped in resonances from which they cannot escape without external perturbation. The Trojans orbit peacefully, accompanying Jupiter for billions of years, their paths determined by three-body dynamics that Lagrange formalized in the 18th century. Neptune also has Trojans, though fewer have been discovered due to Neptune's greater distance and lower brightness. Mars has a handful of Trojans, small asteroids caught in its L4 and L5 points. Though Mars's lower mass makes these positions less stable, objects can escape more easily. Earth may have one quasi-stable Trojan, Asteroid 2010 TK7, which oscillates around Earth's L4 point in a complex trajectory that remains bound for now, but will likely escape within thousands to millions of years. Even Earth's weak gravity can trap objects temporarily, though only Jupiter's immense mass maintains truly stable Trojan populations over billions of years. The planet's composition mostly hydrogen and helium. The primordial gas from which stars form indicates it captured material directly from the solar nebula rather than accreting from solid planetesimals alone. This capture requires forming quickly, within a few million years of the solar system's birth. Before the nebula gas dissipated into interplanetary space, Jupiter likely formed a rocky core first, perhaps 10 to 20 Earth masses, which then accreted gas gravitationally once core mass exceeded a critical threshold. The gas fell inward rapidly, the planet swelling to its current size within less than a million years, becoming gravitationally dominant before other planets finished forming. This early dominance shaped everything that came after. Jupiter's gravity stirred the asteroid belt, preventing planetary accretion. It scattered planetesimals throughout the outer solar system, some becoming the Oort cloud, others ejected to interstellar space. It migrated inward, then outward, possibly triggering the late heavy bombardment. It continues influencing asteroid and comet orbits today, slowly reshaping the solar system through gravitational interactions that accumulate imperceptibly over human lifetimes, but dramatically over geological timescales. Only took a few million years to form, 4 billion years to reshape everything. The planet radiates more heat than it receives from the sun, internal heat left over from formation, plus heat from ongoing gravitational contraction as the planet slowly shrinks. This thermal radiation, though weak compared to sunlight, indicates that Jupiter has not reached thermal equilibrium with space, that it continues cooling slowly, contracting by perhaps 2 centimeters per year, converting gravitational potential energy to heat that radiates into the dark. The process will continue for billions of years until internal temperature drops low enough that contraction ceases, at which point Jupiter will finally achieve equilibrium, cold and stable, no longer generating internal heat. 3I Atlas passes well outside Jupiter's orbit. Its perihelion at 0.645 astronomical units, placing it inside Venus's orbit, nowhere near Jupiter's domain at 5.2 astronomical units. But Jupiter's gravity affects the comet nonetheless, slightly, bending its trajectory by fractions of a degree, changing its velocity imperceptibly, exerting influence across millions of kilometers through gravitational fields that extend to infinity, declining with distance but never reaching zero. The comet will depart the solar system at a slightly different angle than it would have without Jupiter's presence, a perturbation too small to measure but real nonetheless, demonstrating that nothing passes through the solar system truly unaffected by Jupiter's mass. Only took 4.5 billion years for Jupiter to influence everything within dozens of astronomical units. 3I Atlas reaches perihelion in late spring, passing inside Venus's orbit at 0.65 astronomical units from the Sun, its coma blazing at maximum brightness as sublimation accelerates under intense solar heating. The nucleus temperature rises to perhaps 0 Celsius on the sunward side, still freezing by terrestrial standards, but warm enough that water-ice transitions directly from solid to vapor, bypassing the liquid phase entirely in the vacuum of space. Gas streams outward, carrying dust, forming tails that stretch millions of kilometers behind the comet, visible from Earth as a faint smudge moving slowly against the background stars, tracked by observers who understand this is the last time human eyes will ever see this particular object. The comet originates from somewhere beyond the Sun's gravitational influence, from a molecular cloud orbiting some distant star, ejected during planetary formation or scattered by gravitational interactions, set adrift through interstellar space millions of years ago. Its chemistry reflects that other system carbon compounds in ratios slightly different from solar system norms, isotopic signatures that don't quite match local material, organic molecules synthesized in a protoplanetary disk that condensed from gas enriched by previous generations of stars. It carries information about another star system, though the information remains partially encrypted, readable only through spectroscopy. Incomplete even then. Which star? The trajectory. Traced backward through space, points toward the constellation Lyra, but this indicates only direction, not distance. The comet might originate from a star 10 light-years away or 100. Its path bent by encounters with other stars during its interstellar journey. The original ejection velocity and direction lost to gravitational interactions over millennia or millions of years. Even if the parent star were identified, it would appear as just another point of light in Earth's sky, indistinguishable from thousands of others without detailed spectroscopic analysis. Its planetary system, if it still hosts one invisible from this distance, detectable only through careful monitoring for transits or radial velocity variations. The comet knows nothing of its origin. It does not remember ejection, does not carry records of the system it left, does not preserve information about planets that might orbit its parent star or life that might exist on those planets. Just ice and rock, chemistry frozen in time, molecules synthesized billions of years ago now sublimating in this star's light, dispersing into this solar system's solar wind, mixing with local material, becoming indistinguishable from native solar system gas within days or weeks as diffusion and dilution erase its interstellar signature. Observations continue as long as possible. Telescopes in Chile, Hawaii, the Canary Islands, South Africa every clear night, every available instrument, collecting photons reflected or emitted by the comet, measuring brightness, recording spectra, refining trajectory calculations. The data accumulates in archives, available to researchers worldwide, adding to humanity's catalogue of interstellar objects 3 confirmed, dozens more suspected but not proven. Statistical models suggesting hundreds enter the solar system annually, but remain too small or distant for detection. Only took until 2017 to detect the first one. Oumuamua, recognized as interstellar, only after it had already passed perihelion and begun its outward journey. The comet continues brightening through April. May, its coma expanding to perhaps 1 million kilometers across, though this represents gas so diffuse that particles encounter each other only rarely, the density approaching hard vacuum despite the coma's enormous size. The tails lengthen, plasma tail pointing directly away from the sun, dust tail curving slightly backward along the orbital path, both visible in long exposure photographs, though barely perceptible to the naked eye even under dark skies. Most observers require telescopes to see it at all, a faint, fuzzy patch moving slowly night to night, distinguishable from background stars and galaxies only through its motion and slight non-stellar appearance. By June, the comet passes perihelion and begins its outward journey, moving away from the Sun, crossing Earth's orbit at a safe distance several million kilometers, far enough that no gravitational interaction occurs, no perturbation to Earth's motion, no effect on anything except the observations recorded by astronomers who happened to be watching when it passed through. The coma begins shrinking as solar heating decreases with distance, sublimation slowing, gas production declining, brightness fading. Within weeks, it becomes too faint for amateur telescopes. Within months, Only professional observatories can detect it. By year's end, it will have faded beyond the reach of most instruments, visible only to the largest telescopes under ideal conditions. A faint point of light moving against the stars, carrying its interstellar chemistry back into the dark. The comet crosses the asteroid belt outbound, threading through the same sparse field it crossed inbound, encountering nothing, deflecting nothing, passing through as though the belt were empty, which, effectively, it is from the comet's perspective. Millions of asteroids occupy the belt, but they are separated by such vast distances that a comet can cross the entire region without coming within visual range of a single object. Its trajectory determined entirely by the sun's gravity, planetary perturbations too small to measure, asteroid encounters literally impossible at current object densities. By late summer, the comet crosses Mars's orbit outbound, still receding, still sublimating faintly, still visible to the largest telescopes, but fading steadily. Observations become infrequent once per week rather than nightly. The comet no longer bright enough to justify continuous monitoring. Other targets becoming higher priority as this one fades toward invisibility. The final observations occur in autumn, perhaps, captured by automated surveys that image the entire sky repeatedly, detecting the comet as a faint smudge among thousands of other faint smudges, most of them galaxies billions of light-years away. This one merely a visitor from another star system, closer by factors of trillions but still departing, still moving away, its velocity unchanged by its passage through this system. The comet crosses Jupiter's orbit sometime in winter. Invisible now, too distant and too faint for detection. Its coma collapsed back to the nucleus as temperatures drop below sublimation threshold, water ice refreezing on the surface, dust settling back onto the nucleus, the object returning to dormancy after its brief awakening. It continues outward at 47 kilometers per second, faster than any planetary escape velocity. Hyperbolic trajectory carrying it beyond Neptune's orbit over the next few years, beyond the Kuiper belt over the next decade, beyond the heliopause where the solar wind yields to interstellar medium sometime next century. And then it continues. Through the interstellar medium, through molecular clouds, through regions of space where stars lie light-years apart and darkness dominates everything. The comet travels onward, cooling toward the background temperature of space. 2.7 Kelvin, the cosmic microwave background. Thermal radiation left over from the Big Bang, the coldest achievable temperature without active refrigeration. It will travel for thousands or millions of years before encountering another star system, if it ever does. Most interstellar objects wander the galaxy indefinitely, passing between stars without ever being captured, drifting through the dark, alone. Only took a few million years to get here, will take millions more to arrive anywhere else, if anywhere else exists on its trajectory. Earth-based observers note the comet's final position, update trajectory calculations, archive the observations, publish papers analyzing its composition and dynamics, add it to the catalog of interstellar objects detected and characterized. 3. Confirmed now. Eventually, there will be dozens, hundreds, as survey technology improves and detection rates increase. Each one will tell a story about another star system, about planetary formation elsewhere, about chemistry operating under different initial conditions, about the universality of physical laws across the galaxy. But this one, 3I Atlas, will not be observed again. Its story ends here, with its departure, with its return to the dark, carrying chemistry from elsewhere back into elsewhere, indifferent to observers, unaware of observation, following trajectory determined by gravity alone. Only took 4.5 billion years for anyone to notice its passage. The asteroid belt continues its patient orbit, millions of objects drifting through space, separated by distances so vast that collision probabilities measure in millions of years. The belt resembling not a crowded field, but an enormous desert where stones lie separated by kilometers of empty sand. Each asteroid follows its own trajectory, determined by initial conditions set 4.5 billion years ago and subsequently modified by countless small perturbations, Jupiter's gravity pulling from outside, Mars's gravity pulling from inside, radiation pressure from sunlight nudging surfaces, outgassing from sublimating ice-creating tiny thrust vectors, collisions with other asteroids changing velocities by centimeters per second. The mathematics governing these motions has been understood for centuries. Newton's equations refined by Lagrange, Laplace, Poincaré, Hamilton, expressed in multiple equivalent formulations, integrated numerically by computers that calculate positions and velocities forward through time using approximations that introduce errors measured in meters per year for near-term predictions. Errors that compound exponentially for predictions spanning millions of years until chaos makes long-term forecasting impossible. The belt's current configuration can be calculated precisely. Its configuration 1 million years from now remains probabilistic, knowable only statistically. Individual trajectories lost in the fog of sensitive dependence on initial conditions, yet statistical properties remain stable. The belt's total mass will decline slowly as objects migrate inward through resonances or get ejected outward through encounters with Jupiter. But the rate of decline is measured in fractions of a percent per million years, too slow to observe directly. The size distribution, many small objects. Fewer large ones will persist because collisions continue fragmenting large objects into smaller ones, while removing the smallest through radiation pressure or planetary sweeps. The compositional gradient rocky objects inward. Carbonaceous objects outward will remain because no mechanism exists to transport material efficiently between different regions of the belt. Ceres will continue cooling, its hypothetical subsurface ocean slowly freezing from above as internal heat dissipates through radiation and conduction, the process requiring perhaps 1 billion years to freeze completely, though no one can predict exactly because too many parameters remain uncertain: salt concentration, internal structure, radiogenic heating rate, thermal conductivity of the crust. Perhaps liquid water persists for another 1 billion years. Perhaps it froze already, millions of years ago, and current observations sample only the frozen remnant, brines locked in ice, ammonia compounds trapped in minerals, bright salt deposits marking ancient vents where liquid once reached the surface. Only took 4 billion years to possibly maintain liquid, might take 1 billion more to certainly freeze. Vesta will remain geologically dead, its internal heat long since radiated away, its surface unchanging except through occasional impacts that excavate fresh craters, exposing subsurface material that hasn't seen sunlight for billions of years. The enormous basin at Vesta's south pole will persist, slowly accumulating micrometeorite impacts and solar wind erosion, but fundamentally unchanged. A monument to catastrophic collision that occurred perhaps 1 billion years ago. Its ejecta now scattered throughout the inner solar system, some fragments having already collided with Earth as Hidi meteorites, analyzed in laboratories, telling the story of differentiation and disruption. The smaller asteroids, Pallas, Hygeia, Davida, Interamnia, Europa, Sylvia. The thousands of objects larger than 100 kilometers. The millions larger than 1 kilometer will continue their orbits essentially unchanged over timescales relevant to human civilization or even to human species existence. An asteroid orbiting at 2.7 astronomical units with low eccentricity occupies a stable configuration that will persist for billions of years unless perturbed by close encounter with Mars or Jupiter. Encounters that occur rarely enough that most asteroids will never experience one. The belt is stable, mathematically, dynamically, a permanent feature of the solar system until the Sun's evolution changes everything. In 5 billion years, the Sun will exhaust its hydrogen fuel and begin fusing helium in its core, expanding into a red giant that swallows Mercury and Venus. Possibly Earth, certainly rendering the inner solar system uninhabitable as surface temperatures rise to thousands of degrees. The asteroid belt, farther out, will survive this transformation, though temperatures will increase enough that water ice sublimates, organic compounds decompose, surface chemistry changes entirely. The belt will still exist, perhaps unrecognizable but present, orbiting a star that has become something different, larger and redder and dying. Eventually, the Sun will shed its outer layers, ejecting much of its mass into space as a planetary nebula, leaving behind a white dwarf core, a dense ember the size of Earth containing half the Sun's original mass, slowly cooling over trillions of years. The asteroid belt, reduced in mass by the Sun's mass loss, will drift outward, its orbits expanding as gravitational binding weakens. Objects will become unbound, escaping to interstellar space, joining the population of wandering asteroids and comets that drift through the galaxy, occasionally passing through other star systems as interstellar visitors, carrying chemistry from this solar system into others. Unobserved, undetected, insignificant. Only took 10 billion years from formation to dissolution, but that remains far future, distant enough that predictions become meaningless, conditions so different from present that extrapolation fails. For now, for the next billion years, certainly. For the next several billion years, probably. The asteroid belt continues as it has continued, orbits proceeding according to gravitational mathematics, collisions occurring at rates measurable in impacts per million years, migration happening slowly enough that configurations remain essentially stable over timescales relevant to Earth's biosphere. The belt serving as both reservoir of primitive material and source of near-Earth objects that occasionally threaten but more often miss, that deliver water and organics but also extinction-scale impacts, that represent both danger and origin, both threat and memory. The belt remembers the solar system's formation, preserves material unchanged since the solar nebula collapsed, offers samples of earliest chemistry available for study whenever fragments migrate inward and fall to Earth as meteorites. It represents the solar system's attic, a storage space filled with objects too valuable to discard but not useful in daily planetary operations, material set aside during formation and never incorporated into planets, waiting patiently in orbit for someone to examine it, study it, learn from it what conditions prevailed 4.5 billion years ago when everything began. 3I Atlas has departed, carrying its interstellar chemistry back into the dark, its brief passage through this system complete, its observations archived, its trajectory calculated for as long as observations permit, years or decades depending on how long it remains visible. Eventually it will fade entirely, distance and dimness rendering it undetectable even by the largest telescopes, its position known only approximately, its continued existence inferred but not confirmed, lost to observation though still traveling, still cooling, still moving away at 47 kilometers per second, still following the hyperbolic trajectory determined by its arrival velocity and the Sun's gravitational influence, unchanged by anything encountered here, unaffected by anything except gravity. The solar system remains essentially unchanged by its passage, no orbits perturbed significantly, no objects deflected, no chemistry altered, nothing impacted or disturbed. Just observations collected, data archived, knowledge gained about interstellar objects and their properties, confirming that other star systems produce comets similar to local ones, that planetary formation operates similarly elsewhere, that chemistry follows the same rules throughout the galaxy, that this solar system is not unique or special, but typical, one among billions, producing the same objects through the same processes, governed by the same physics. Only took 3Y Atlas a few months to pass through, a few months to teach that lesson, an eternity to carry it elsewhere. The silence returns. The deep silence of space where no sound propagates, where objects drift through vacuum without friction or resistance, where motion continues unchanged for millions of years because nothing exists to slow it. Nothing pushes back. Nothing resists. The asteroid belt orbits in this silence. Millions of objects following trajectories calculated by gravity alone, moving at speeds of 20 kilometers per second relative to the Sun, but appearing motionless when observed from Earth, their positions changing imperceptibly night to night, requiring weeks or months of observation to detect motion against the background stars. Time passes differently here than on planetary surfaces. No seasons mark the years, no weather changes the conditions, no erosion reshapes landscapes. A boulder resting on an asteroid's surface might remain undisturbed for 1 billion years, touched only by micrometeorite impacts too small to move it, warmed and cooled by the sun's rise and set every few hours as the asteroid rotates, otherwise unchanged, waiting. The patience of stone, multiplied by the patience of vacuum, equals a stillness that approaches the eternal. Darkness dominates. The sun appears bright from the asteroid belt, far brighter than the full moon appears from Earth, but it remains a point source, casting sharp shadows, leaving regions not directly illuminated in complete darkness, punctuated only by starlight and the faint glow of the Milky Way. An observer standing on an asteroid's surface would see stars by the thousands. The galaxy stretched across the sky, planets bright and steady against the stellar background, and nothing else. No atmosphere scatters light, no clouds obscure the view, just darkness and stars and the slow wheeling of the celestial sphere as the asteroid rotates. The mathematics continues computing itself, gravity pulling on each object according to its mass and distance, trajectories evolving through time, resonances maintaining their positions, gaps remaining empty, clusters remaining clustered. The belt requires no maintenance, no adjustment, no intervention. It simply is, continuing as it has continued, as it will continue, patient and indifferent, a feature of this solar system as permanent as the planets themselves, as lasting as the sun. Sleep approaches, perhaps, or something like your sleep a quieting of observation, a cessation of tracking, a return to unknowing where the belt exists unobserved, its objects orbiting without witness, their positions uncalculated, their futures undetermined by any computation except the universe's own slow working out of gravitational equations across billions of years. The stones drift onward, alone together in the dark, separated by distances too vast to cross, but bound by the same star's gravity. Family members who never meet but share a common origin, a common fate, a common silence that extends across millions of kilometers and billions of years, unchanged and unchanging, patient beyond measure, still.